In this video, we are learning about the Doppler effect. We will start with the basic introduction of Doppler effect, what is Doppler effect and what is formula of Doppler effect. Then later on, I will derive the formula for all the four conditions which are there, which affect the frequency of sound. And then at the end, we will solve a few questions. So the very first thing is, what is Doppler effect? So Doppler effect is the phenomena which is related to change in observed frequency of sound. Observed frequency. So actual frequency remains same here, and the observed frequency changes. So why it's named Doppler effect? Because this phenomena was explained by Christian Doppler. Christian Doppler. He was born in Austria in 1803, and he was physicist as well as mathematician. What happens in case of Doppler's effect is, either the source is moving towards the observer. Let's say this is source and here is observer, or the observer is moving towards the source, or source is moving away from the observer, or observer is moving away from source. So these are the four conditions which we are going to explore, but it's not limited to only these four conditions. Sometimes source and observer, they both may be moving together in different directions or towards each other. So for simplicity, we are going to discuss only the four conditions, and I'll discuss what are those four conditions. First, let's write the formula, because some of you may not like to watch the whole video, so you can note down the formula. So the formula to calculate the change in observed frequency due to the relative motion between source and observer could be given as f dash is equal to f v plus v naught divided by v plus v s. Now this formula is very limited because I have written only plus in numerator as well as in denominator. So if I have to apply this formula in all the conditions, all the four conditions, which I'll discuss in few seconds, so I have to add one more thing, negative sign. So let me take a different color, and here is negative sign in both numerator as well as in denominator. Now if you want to write this formula for each condition, then it could be written as, when source is stationary and observer is moving. So I can write f dash is equal to f, and since source is stationary, here vs is speed of source. So when source is stationary, speed of this source becomes 0. We can write v plus minus v naught divided by v. And now second condition could be, when source is moving and observer is stationary. So in that case, I can write f dash is equal to f v. Now v naught here is velocity or speed of observer. Sometimes we say v0 also, but technically it's read as v naught. So f dash is equal to f v divided by v plus minus v s. So now what you can see is, in case of stationary source, v naught is there, but vs is not there in the denominator. And in case of moving source and stationary observer, v naught disappeared and only vs is there. Okay, of course, v, which is speed of sound, is always there. So here v is speed of sound, for your information. Now let us start deriving these formulae in detail. So the first condition is, when source is moving towards the observer, now imagine you have a source here. This is S and this is observer O, and the observer is stationary and source is also stationary initially. Imagine. So what you can write here, let me draw the diagram first for the sound wave. So sound wave is traveling like this and reaching towards the observer. Once the source starts moving either towards the observer or away from the observer, then the observed frequency, which is reaching towards the observer, will change. So the sound wave has some characteristics. Let's write that first. So first thing here, sound has speed. So speed of sound is v here. Throughout the derivation, I will be using v for the speed of sound. Speed of source is vs, and sound has frequency f. Frequency of sound is f, and this frequency is emitted by the source. Wavelength, original wavelength. So here, to be very specific, original wavelength is lambda. So these are the things before observer hears the changed frequency. Now original wavelength is lambda, and another important thing is time period. Time period. Now let us derive the formula for when the source is moving towards the observer. And I will go to the next slide, and let me remove this part to save the space. Yeah, I got some extra space now. So here is my source and here is the observer. Now I have discussed in the last slide what was the frequency, wavelength, speed of the sound and the speed of source. Now let's directly come to the discussion. As the source is moving towards the velocity, towards the observer with velocity vs, the first pulse which is emitted from this source let's say this is the first pulse, very first pulse. First pulse. It will start going with speed v, which is the speed of sound, towards the observer. It will take some time t to complete one wavelength here. It will reach from the source to a certain distance, and it will take time capital T. Now if the source is moving with velocity Vs, which is something like this, so in same time capital T, the source will also cover some distance. So first of all, distance covered by the wave, how much it would be? D is equal to velocity of wave into the time period. Now if you see carefully, then you can say velocity into time period is equal to distance, and this is the distance for one cycle, because wave completes one cycle in one t, capital T, right? So here we can write lambda is equal to d, which is equal to vt. But as this source is also moving with certain velocity, which is given to us, so let me draw a new diagram. Imagine this is the beginning or the initial condition when the source is emitting the sound and sound is traveling forward. Sound reached here, here, and source will emit the next pulse when sound is reaching here. But the thing is, the source also covered certain distance with velocity Vs, and in time t the source may have reached to a new position. So this is new position where second pulse would be generated. So at this point, the second pulse is getting generated. Actually, if the source was stationary, the second pulse would have been generated here for stationary source. But the second pulse is getting generated somewhere else. And the motion of source is not going to affect the motion of sound. So sound will go with its own speed and it will cover certain distance in the given time period. Right? Here is the time period. Now the distance, the question is, what is distance covered by the source? So distance covered by the source, ds is equal to vs into t. Why I am taking capital T? Because until and unless the second pulse is generated, the wave, the observer is covering certain distance. Okay, and the moment second pulse is generated, now it will be the distance between, it will become the wavelength, and it will be the new wavelength between these 2 points here. So this is the new wavelength, which we will later on say observed wavelength, lambda dash. Let me go on the next slide, and on next slide we will discuss. So here once again, distance covered by the source, ds is equal to vs into t, and distance covered by the sound d is equal to vt. So for simplicity and for reference, I will draw the diagram once again here. Initial position, here sound after time t, and new position of source, new position of source after time t. And this is ds, this is d. So what is the new wavelength, or you can say the distance between the current position of source and the first pulse? This is first pulse, if you remember, and this is second pulse. Second pulse. This distance between the current position of the second pulse and the first pulse is called as lambda dash, and we can find lambda dash by using formula lambda by using the formula which we just found in the last slide, which is lambda dash is equal to d minus ds. So I can write here lambda dash is equal to d is v into t minus ds is vs into t. So lambda dash is equal to v minus vs into t. So as the wavelength has changed, speed of sound is not going to get affected. So frequency must change. So observed frequency of sound f dash would be v by lambda dash. And what is v here? V is the speed of sound, and lambda dash is the observed wavelength or the new wavelength which is happening because of the speed of the source. So we can write here v by v minus vs into t. Now t is the time period and it's in the denominator, so you can write it as v by v minus vs into 1 by t. And you know 1 by t is frequency, so you can write f dash is equal to v by v minus vs into f. So here we are getting the formula for the observed frequency of sound when source is moving towards the observer, when source is moving towards the observer with velocity vs. Please take a note of this. You can, if you want, you can pause the video and you can write the formula, everything. Now let us go on the next slide, and just for better understanding, you continue writing in your notebook along with me, and if you want, you should pause the video as well and then proceed. Let's go to the next condition. And next condition, let me write here the heading as it's asking. So the heading is when the source is moving away from the observer. So when source is moving away from the observer, let me adjust just 1 second. Yeah, this is one. when the source is moving away from the observer, derivation would be exactly same. There will be not much change. Derivation would be almost same. The only thing would be, because the source is moving away. So what we did here in this last slide, here lambda dash is equal to d minus ds. In place of this, we have to use just plus, because the distance will increase. So instead of subtracting, we have to add d plus ds. That would be the only change. So here, when the source is moving with velocity vs away from the observer, here is the observer O, and this is source. So what would happen? Because the observer is moving away, in time t, it will reach to a new position. Let's say this is the new position. So what happened? When the first pulse reached here at the observer, and now the second pulse was supposed to be emitted at this point, but it's not emitting here because the source is shifting, and in time t it will cover some distance, let's say that is ds, and it will reach here. When the source is reaching here, the second pulse is just emitted. So this is second pulse. And when the second pulse is emitted, you can see the distance between the first pulse and the second pulse. So what is distance? ds plus d. Now this is the new wavelength, lambda dash. Right? So lambda dash is equal to d plus ds, and if you do everything like in the last slide, you can write f dash is equal to v by vt plus vst, and f dash is equal to v by v plus vs into 1 by t. And 1 by t is frequency. You can write f dash is equal to f v by v plus vs. This is the formula for change in frequency, observed frequency when the source is moving away from the observer. You can take a note of this. Let me create the another slide for you. Just 1 second. And here we are. Now in this case, what we are going to discuss is, we are going to discuss about the when this source is stationary but the observer is moving. So here observer is moving towards the stationary source. So the condition is, now the observer is moving and the source is stationary. Let me change the color of the pen. I'll come to the last pen used. So here, this is our source and here is the observer. Observer is now moving towards the stationary source. But for simplicity, let us start from very beginning. This is the pulse which is given by the source, and the pulse is reaching towards the observer. Here is the pulse received by the observer, this pulse. As the observer receives the pulse, hears a sound, right? Now, when the observer starts moving towards the source with velocity, let's say velocity of the observer is v0, then the thing is, observer will catch more pulses in less time, because If this is the first pulse heard by the observer, now the second pulse will take some time to reach here. An observer has to wait to hear the second pulse. But observer is now very curious and running towards the source. So what will happen? As the observer is also running towards the source, the pulse will be here in between the path only, but the ear of the observer or the any receiver will immediately detect the next pulse in between the path only. So what happened? Earlier, the time taken by the pulse was longer. Now the time taken by the pulse is small. Actually, there is no change in the timing of the pulse, but it seems to the observer that the pulse is reaching faster to the observer, right? So here is the situation, and I'll try to draw it from very beginning, like source and observer, right? Observer, the first pulse is emitted the moment first pulse is reached here to the observer. First pulse, the observer heard the first pulse, okay, imagine, and immediately, not he's not wasting any time, immediately started moving towards the source. Second pulse will be emitted after time t, right? Second pulse will be emitted after time t, and it will take some time to reach to the observer. And it's as the first pulse reaches to the observer, second pulse is emitted, and now it's on the way towards the observer with velocity v, which is velocity of the sound, right? And this observer has also started his journey with velocity v naught. Since they both are in motion, pulse and observer, it's possible that they meet somewhere here. They can meet somewhere here. So at what time, the question is at what time they will meet, they will meet. And that will depend on the relative velocity between the source and between the sound emitted by the source and the observer, right? So speed of sound is v, so I can write the relative velocity of sound with respect to the observer would be v plus v naught. For the observer, it will appear that the sound is now moving faster because each pulse is moving at higher speed, and it's reaching faster towards the observer. Actually, it's not happening, but it's a observer who is feeling that pulses are reaching faster because the speed of observer is getting added in the speed of sound, okay. And this is the concept of relative velocity. Let me add a new slide, and we will discuss there. Yeah, this should go. Not required. Not required. Okay. So now, what is frequency? Which is observed by the observer, because the velocity and relative velocity of the sound has changed. So we can write here f dash is equal to f dash is equal to v by lambda. Wavelength of wave is not changing. Wavelength remains same. But due to motion of the observed velocity is changing. So here this time, unlike the source was moving, we are going to use the concept of relative velocity here. So I will write here VR. VR, just for simplicity, relative velocity. Relative velocity. Oh, relative velocity. So f dash is equal to what we have written just now. We have written v plus v naught. Is it v plus v naught? Yes, v plus v naught divided by lambda. And we know lambda is equal to that formula we can use, right? V is equal to f lambda. So lambda is equal to v by f. So let us substitute this value here. So what should we get? We should get v plus v naught divided by v divided by f. And this is in denominator. So we can take the reciprocal of this value here. So after simplification, it will become v plus v naught divided by v into f. Now this f is the original frequency of sound, and here is the observed frequency, right? So now you can see how we can derive the formula of formula of change in frequency, observed frequency, pardon me, formula of observed frequency when the source is stationary but the observer is moving towards the stationary source. Now the next condition is one more slide. Next condition is when observer is moving away from stationary source. When observer is moving away from stationary source. So when observer is moving away from the stationary source, the only change we can do here is in the relative velocity. So here is this source. Here is the observer, and these are the pulses which are getting emitted and reaching to the observer. And the moment this first pulse reaches here, first pulse reaches to the observer starts running away from the source with velocity v naught. Now when the observer starts running away from the source, this pulse will reach here, then it has to travel some more distance to catch or to reach to the observer, right? So in that case, the relative velocity between the source and the observer appears like decreased velocity. For the observer, it will appear that the sound which is coming or the pulse which is coming towards the observer, it's traveling slowly. So the relative velocity between source and observer is v minus v naught. Now rest of the things will remain as it is, and you can find f dash is equal to, I'll do it quickly, v minus v naught by lambda is equal to v minus v naught by v into f. F is the observed frequency. So now we got all the four formulae which are required for solving the questions related to the Doppler effect. And let me summarize those formulae in the next slide. And they are, I don't need this, not even this. So they are, first one, F dash is equal to F V by V plus Vs. And this is the formula for when the source is moving towards the observer. When source is moving towards the no, this is the formula for when the source is moving away from the observer. Pardon me. This is the formula when source is moving away from the observer. Away from observer. So the first form. So the first formula. So the first formula is when the source is moving towards the observer. When the source is moving towards the observer and the observer is stationary, and we can write f dash is equal to f v by v minus vs. And second one, when the source is moving away from the stationary observer, and here it's a f dash is equal to f v by v plus vs. And the third one is when the source is stationary but the observer is moving towards the source. Observer is moving towards the source, and we can write f dash is equal to f v plus vs v plus v naught divided by v, and f dash is equal to f v minus v naught by v. And the last one, this is fourth one, is for when the source is stationary and the observer is moving away from the source. So these are the four formulae which we have just derived, and we understood this in detail. Now let's go and solve one question. I have picked three questions for you guys. You can pause the video and read these three questions if you want, and then we will solve one of the question which is given to us. So let's copy and paste this question on the next slide. I'll take the first one. And here is the question I'm pasting here. I don't want this click to add a title. I'm deleting this part. I don't need this. Let's arrange this a little bit upward, yes, and just creating space for my writing. Okay, so the things which are given to us is ambulance is moving towards an observer with a speed of 50 km per hour. So speed is given to us is 50 kilometer per hour, and this is the speed of source or the observer. This ambulance is moving towards the source, and ambulance is emitting the sound. It means this is Vs, right? So here we have added this Vs is equal to 50 kilometer per hour, and the speed of sound is given to us 340 meter per second, and the frequency is given to us f is equal to 100, not 100, pardon me, 1000 hertz. So which formula should we use to solve this question? We have derived 4 formulae in the last slide and in overall video, and you can refer all the 4 formulae in the video, and we can use the formula when the source is moving towards the observer. That is, f dash is equal to f v by v minus vs, and you know what is f dash, f and v minus vs. Now the thing is, I can directly substitute the values and I will get some answer, but the problem is it would not be correct answer because the units are different. This one is in meter per second, this one is in kilometer per hour. So let me convert it into meter per second. So what we can do to convert kilometer per hour, we multiply by 5 by 18, and when we multiply it by 5 by 18, we get 250 divided by 18, and if you simplify using calculator, you can use calculator, and I'm also using here, it will give me around 13.88. So roughly I can use 14 meter second power minus 1. This is my speed which I'm getting, and it's a speed of the ambulance, right? Now v is equal to 340 meters. Everything is properly aligned, so I can write f dash is equal to f v, which is 340 divided by 340 minus 14. Let's create some space here, and here we can write f dash is equal to 100, not 100, pardon me, 1000 into 340, and 340 minus 14 is 326. Let's simplify it using a calculator. So you are going to get 1000 into 1.042 hertz. So if you multiply 1000 with it, you will get 1042 hertz. This is the observed frequency of sound by the observer who is standing on the road, who is standing on the road. Okay, continue solving rest of the questions which are given in this slide, and you can search more questions, and if you want I can add more questions in the comment section or the description. You can go and check the questions and solve it. See you.